August 8, 1944. Villers-Bocage, Normandy. German 101st Heavy Tank Battalion Command Post. Oberst Friedrich von Stauke set down his morning coffee and stared at the after-action report that would shatter the myth of German armor invincibility forever. The words were precise, devastating, and would never appear in any official Wehrmacht communiqué. Tiger 007 destroyed by enemy anti-tank fire. Penetration through frontal armor plate at range 800 meters. Crew, total casualties. What none of the assembled German tank commanders knew was that this single combat report would reveal the mathematical superiority of British ballistics over German metallurgy, proving that the despised Sherman Firefly, with its 17-pounder gun, had just accomplished what Allied forces had been unable to achieve for 2 years: reliable destruction of German heavy tanks through frontal armor penetration. The report contained forensic analysis, ballistics calculations, and metallurgical evidence that challenged every assumption about German technological superiority in armored warfare. While German engineers had created the world's most heavily armored tanks, British ordnance specialists had perfected the mathematics of armor penetration through systematic application of physics principles that rendered armor thickness irrelevant when confronted with sufficient kinetic energy delivered by precision-manufactured projectiles. In the smoky atmosphere of the command bunker, surrounded by tactical maps showing the positions of surviving German armor, the most experienced tank commanders in the Wehrmacht would confront a reality that contradicted everything they believed about armored combat, crew survival, and the technological advantages that had sustained German offensive operations since 1939. The war they thought they were winning through superior engineering was about to become a deadly contest of mathematics versus metallurgy, where British calculations would prove more lethal than German craftsmanship. By August 1944, the Western Front had evolved into the ultimate testing ground for competing philosophies of tank design, where German emphasis on heavy armor and powerful guns faced Allied approaches that prioritized numerical superiority, mechanical reliability, and tactical flexibility. The Sherman tank, initially dismissed by German commanders as inferior American engineering, was about to be transformed into a tiger-killing weapon through systematic application of British ballistics expertise. The German Panzer had dominated European battlefields for 5 years through tanks designed around principles of individual superiority. Thicker armor, more powerful guns, and sophisticated mechanical systems that gave German crews decisive advantages in direct combat. The Tiger I heavy tank represented the ultimate expression of this philosophy, mounting the legendary 88mm gun behind armor protection that could withstand hits from most Allied anti-tank weapons. German tank doctrine emphasized quality over quantity, assuming that superior individual tank performance would compensate for numerical disadvantages through higher kill ratios and battlefield survivability. Tiger tanks had achieved kill ratios exceeding 10-to-1 against Allied armor during 1943-1944, validating German assumptions about the effectiveness of heavy armor and powerful guns in sustained combat operations. But numerical superiority was beginning to overwhelm individual excellence, as Allied production delivered thousands of Sherman tanks to European battlefields. The mathematical equation was shifting. Even superior German tanks could be overwhelmed through concentrated attacks by multiple Allied vehicles, especially when Allied crews learned to exploit German tactical limitations and mechanical vulnerabilities. The introduction of the Sherman Firefly represented a fundamental change in this equation. British ordnance specialists had recognized that defeating German heavy armor required not just more tanks, but better guns capable of penetrating Tiger armor at combat ranges. The 17-pounder anti-tank gun had been developed specifically for this purpose, utilizing advanced ballistics principles and sophisticated ammunition design to achieve armor penetration performance that exceeded German expectations. Most significantly, the Firefly program demonstrated Allied ability to adapt existing tank designs to incorporate superior firepower without requiring complete vehicle redesign. While German engineers were developing increasingly complex and expensive tanks, Allied engineers were systematically improving proven designs through incremental modifications that enhanced combat effectiveness while maintaining production efficiency and mechanical reliability. German tank development reflected cultural and military values that emphasized individual excellence, technological sophistication, and mechanical superiority over mass production efficiency. The Tiger tank embodied this philosophy through engineering decisions that maximized armor protection and firepower while accepting complexity that limited production speed and operational reliability. Dr. Ferdinand Porsche had approached heavy tank design with scientific precision that optimized armor effectiveness within weight limitations imposed by available engine power and transmission technology. Tiger armor incorporated advanced metallurgical techniques, sophisticated heat treatment processes, and thickness specifications that provided protection against all known Allied anti-tank weapons when the design was finalized in 1941. The Tiger's construction utilized high-quality steel alloys, precision manufacturing techniques, and quality control standards that ensured consistent protection characteristics across all production vehicles. Armor plate was manufactured using advanced rolling processes that achieved optimal hardness to ductility ratios, preventing both penetration and catastrophic failure when struck by enemy projectiles.
Most critically, German armor design philosophy assumed that thickness was the primary determinant of protection effectiveness. Tiger frontal armor measured 100 mm thickness, angled to provide effective protection equivalent to 140 mm against most projectile types. This protection level had proven adequate against all Allied tank guns and most dedicated anti-tank weapons encountered during 1942 to 1943. Oberst Heinz von Westernhagen, commanding the 101st Heavy Tank Battalion, had developed tactical doctrine that maximized Tiger advantages through long-range engagement, where superior German guns could destroy Allied tanks before enemy weapons could achieve effective hits. German crews were trained to engage at ranges exceeding 1,500 meters, where 88 mm armor-piercing projectiles could penetrate most Allied armor while remaining immune to return fire. This tactical approach had achieved devastating success during defensive operations in Italy and the early phases of the Normandy campaign. Tiger tanks could dominate entire sectors through superior firepower and protection, achieving kill ratios that validated German confidence in armor superiority and crew training advantages. But tactical doctrine designed around armor invulnerability would become catastrophically vulnerable when confronted with Allied guns capable of defeating German protection at combat ranges. The entire German tactical system assumed that Allied weapons could not achieve reliable frontal penetration against Tiger armor, an assumption that British ballistics specialists were systematically preparing to invalidate. While German engineers focused on maximizing armor protection, British ordnance specialists had implemented systematic ballistics research programs designed specifically to defeat German heavy armor through superior projectile velocity, advanced ammunition design, and precise mathematical calculation of armor penetration requirements. Major General Percy Hobart had directed the development of specialized anti-tank weapons that prioritized armor penetration over traditional artillery considerations. The 17-pounder gun represented revolutionary approaches to anti-tank warfare that emphasized kinetic energy projectiles achieving maximum velocity rather than explosive shells designed for area effect. The 17-pounder design incorporated advanced metallurgy for barrel construction, sophisticated chamber pressure management, and projectile design optimized for armor penetration rather than explosive effectiveness. The gun could achieve muzzle velocities exceeding 2,900 feet per second with armor-piercing projectiles, generating kinetic energy levels that exceeded German armor protection capabilities at combat ranges. Most significantly, British ordnance development had systematically analyzed German armor protection through captured vehicles, metallurgical testing, and mathematical modeling of penetration physics. This analysis revealed that German armor, while thick and well-manufactured, possessed vulnerabilities that could be exploited through projectiles designed with specific velocity and mass characteristics. Dr. William Penny, directing ballistics research at the Royal Arsenal Woolwich, had calculated precise requirements for defeating 100mm German armor at ranges up to 1,000 meters. His mathematical analysis indicated that projectiles achieving specific kinetic energy levels could penetrate German armor regardless of thickness, providing the foundation for 17-pounder ammunition development. The British approach represented systematic application of physics principles to military problems, utilizing scientific method rather than engineering tradition to develop solutions. While German armor development relied on incremental thickness increases, British gun development focused on mathematical optimization of projectile performance characteristics. Quality control and British ammunition manufacturing ensured consistent ballistics performance that allowed reliable armor penetration at specified ranges. Each 17-pounder projectile was manufactured to precise specifications that guaranteed performance within mathematical parameters calculated for German armor defeat. Direct technical comparison between German Tiger armor and British 17-pounder ammunition revealed fundamental differences in approach that reflected broader strategic philosophies about armored warfare. The comparison demonstrated how mathematical optimization could overcome engineering excellence through systematic application of physics principles. The Tiger I incorporated frontal armor measuring 100mm thickness, manufactured using high-quality German steel, with hardness ratings optimized for projectile deflection and energy absorption. The armor was angled at 9 degrees from vertical, providing effective thickness of approximately 102mm against projectiles striking at normal incidence angles. German metallurgy achieved hardness levels of 550 to 600 Brunel, representing excellent protection characteristics. The 17-pounder gun fired armor-piercing capped ballistic cap APCBC projectiles weighing 17 pounds at muzzle velocities of 2,900 feet per second. These projectiles generated kinetic energy levels of 3,200 foot-pounds at the muzzle, declining to approximately 2,400 foot-pounds at 800 meters. Mathematical analysis indicated that this energy level could defeat German armor at ranges up to 1,000 meters under optimal conditions. The ballistics comparison revealed that British projectile design had achieved penetration capability that exceeded German armor protection by significant margins. While German engineers had focused on maximizing protection thickness, British ordnance specialists had optimized projectile performance to defeat specific armor thicknesses through kinetic energy concentration. Ammunition design differences were critical to penetration effectiveness. German armor-piercing projectiles emphasized weight and explosive filler over velocity optimization, achieving adequate penetration against lighter Allied armor but lacking the kinetic energy necessary for reliable heavy armor defeat. British projectiles prioritized velocity and penetration characteristics over explosive content.
Most significantly, British ballistics testing had identified optimal impact angles and projectile design features that maximized armor penetration effectiveness. The APCBC projectile incorporated a ballistic cap that prevented deflection, an armor-piercing cap that concentrated kinetic energy, and a core design optimized for maintaining penetration capability after initial armor contact. Quality control in British ammunition manufacturing ensured that each projectile met ballistic specifications necessary for reliable armor penetration. German armor quality, while excellent in absolute terms, could not compensate for the systematic advantage provided by British mathematical optimization of projectile performance characteristics. The Sherman Firefly represented Allied ability to adapt existing tank designs to incorporate superior firepower without requiring complete vehicle redesign. British engineers had systematically modified American Sherman tanks to mount the 17-pounder gun, creating a tank destroyer capable of engaging German heavy armor on equal terms. Major George Brighty had directed the Firefly conversion program through systematic analysis of Sherman chassis capabilities and 17-pounder gun requirements.
The modification required extensive turret redesign, recoil system enhancement, and ammunition storage reconfiguration while maintaining overall vehicle reliability and operational characteristics. The conversion process eliminated one crew member to provide space for 17-pounder ammunition storage, accepted reduced ammunition capacity compared with standard Sherman tanks, and required modifications to turret traverse mechanisms to accommodate the longer gun barrel. These compromises were accepted to achieve the armor penetration capability necessary for engaging German heavy tanks effectively. Production planning had organized Firefly conversions to provide approximately one modified tank per Sherman squadron, ensuring that every Allied tank unit possessed anti-tank capability adequate for German armor destruction. This distribution strategy maximized tactical flexibility while minimizing production complexity and resource requirements. Tank crews selected for Firefly operations received specialized training in long-range gunnery techniques, armor identification procedures, and tactical methods optimized for anti-tank operations. Firefly crews were trained to engage German armor at maximum effective ranges, utilizing superior British gun performance to achieve first-hit kills before German tanks could respond effectively. Most importantly, Firefly development demonstrated Allied systematic approach to problem-solving that identified specific tactical requirements and developed technical solutions through incremental modification rather than complete redesign. While German tank development emphasized revolutionary advancement, Allied development focused on practical improvement of proven systems. The mathematical result was tank destroyer capability that could defeat German heavy armor through superior firepower while maintaining the mechanical reliability, production efficiency, and tactical flexibility that characterized Allied armored operations throughout 1944-1945. British military intelligence had compiled comprehensive assessments of German armor capabilities that provided the technical foundation for 17-pounder gun development and Firefly deployment strategies. Intelligence analysis revealed specific vulnerabilities in German tactical doctrine that could be exploited through superior Allied firepower. Brigadier Kenneth Strong, directing intelligence analysis for 21st Army Group, had assembled detailed information about German Tiger tank performance characteristics, armor protection specifications, and tactical employment methods. This analysis provided precise requirements for Allied anti-tank weapons necessary to achieve reliable German armor destruction. Captured German documents revealed Tiger tank production numbers, crew training standards, and operational capabilities that allowed British planners to calculate optimal deployment strategies for Firefly tanks. Intelligence indicated that German heavy tank strength was limited by production constraints and crew availability, suggesting that systematic destruction of individual Tigers would have significant strategic impact. Technical intelligence about German metallurgy had been developed through analysis of captured vehicles, projectile testing against representative armor samples, and mathematical modeling of protection effectiveness. This analysis confirmed that German armor, while well-designed, could be defeated through projectiles achieving specific velocity and mass characteristics. Battlefield intelligence from Normandy operations had identified specific German tactical patterns that could be exploited by Firefly crews trained in long-range anti-tank operations. German Tiger tactics emphasized defensive operations from prepared positions, providing opportunities for Allied forces to engage at ranges where 17-pounder guns achieved optimal effectiveness. Prisoner interrogations revealed German confidence in Tiger armor protection and tactical superiority, suggesting that psychological shock would be significant when Allied weapons achieved reliable armor penetration. German crews had been trained to assume armor invulnerability, creating tactical vulnerabilities that could be exploited through unexpected penetration capability. The intelligence assessment concluded that systematic deployment of Firefly tanks could achieve tactical surprise while providing the armor penetration capability necessary to defeat German heavy tank advantages through superior firepower rather than numerical superiority alone. The initial combat engagements between Sherman Firefly tanks and German Tigers occurred during the Normandy campaign, when British armored units encountered German heavy tanks in tactical situations that would test the effectiveness of 17-pounder armor penetration capabilities under combat conditions. July 12, 1944, Operation Goodwood, Cagney Ridge. Sergeant Joe Eakins, commanding Sherman Firefly Fury, achieved the first confirmed Tiger kill by 17-pounder gun when his tank engaged 3 German Tigers at ranges between 800 and 1,200 meters. The engagement demonstrated both the effectiveness of British armor penetration technology and the psychological impact on German crews who had previously considered their armor protection adequate against all Allied weapons.
Eakins' first shot struck Tiger 007 in the frontal armor at 800 meters range, achieving complete penetration that resulted in immediate ammunition detonation and total vehicle destruction. The German crew had no opportunity for escape, having been trained to assume that frontal armor provided absolute protection against Allied tank guns at combat ranges. The ballistics analysis of the engagement confirmed British calculations about 17-pounder penetration capability. The APC-BC projectile had struck the Tiger's frontal armor plate at optimal impact angle, concentrated kinetic energy through the armor-piercing cap, and achieved complete penetration with sufficient residual energy to cause catastrophic internal damage that eliminated crew survival opportunities. German after-action reports from surviving Tiger crews indicated complete surprise at Allied armored penetration capability. German crews had been trained in tactical doctrine that assumed frontal armor invulnerability, making them vulnerable to Allied guns capable of defeating protection systems that German doctrine considered impenetrable. Oberst Michael Wittmann, Germany's highest-scoring tank ace with 138 confirmed kills, was present during several early Firefly encounters and submitted reports that acknowledged Allied armor penetration capabilities for the first time. Wittmann's assessments indicated that German tactical doctrine required immediate revision to account for Allied weapons that could defeat Tiger armor at combat ranges. The psychological impact on German tank crews was profound and immediate. For the first time since 1941, German armored forces faced enemies equipped with weapons capable of reliable frontal armor penetration. The invulnerability that had sustained German crew confidence was eliminated through systematic application of British ballistics expertise. As Firefly encounters increased throughout August 1944, German armor commanders began recognizing that Allied anti-tank capabilities had evolved beyond German protection systems. Statistical analysis of tank losses revealed patterns that challenged fundamental assumptions about German armor superiority and tactical invincibility. August 20, 1944, Falaise Pocket Operations. German tank loss rates had increased dramatically during operations against Allied forces equipped with Firefly tanks. Statistical analysis indicated that Tiger losses to frontal armor penetration had increased from 0% in early 1944 to over 40% during August operations. The trend suggested that German armor advantages were being systematically negated by Allied firepower improvements. General Major Heinz von Luttwitz, commanding Panzerlehr Division, submitted tactical assessments that acknowledged the effectiveness of Allied armor penetration technology. His reports indicated that German crews were losing confidence in armor protection and beginning to modify tactical procedures to minimize exposure to Allied anti-tank fire. Tank crew interviews revealed psychological stress levels that had not been observed during previous campaigns. German crews who had operated with confidence in armor invulnerability were now experiencing anxiety about Allied penetration capabilities that could defeat protection systems previously considered impregnable. Technical analysis of destroyed German tanks confirmed the ballistics effectiveness of British 17-pounder ammunition. Forensic examination revealed that Allied projectiles were achieving complete armor penetration with sufficient residual energy to cause catastrophic internal damage that eliminated crew survival opportunities. More disturbing for German commanders was evidence that Allied crews were achieving first-hit kills at ranges that exceeded German expectations about enemy gunnery capabilities. Firefly crews were demonstrating accuracy standards that matched or exceeded German crew performance while utilizing weapon systems that provided decisive firepower advantages. The escalating crisis was compounded by production constraints that prevented replacement of destroyed Tigers at rates necessary to maintain unit strength. Each Tiger lost to Allied anti-tank fire represented irreplaceable combat capability that could not be compensated through increased production or crew training improvements. German technical analysts had compiled comprehensive assessments of Allied armor penetration capabilities that revealed the mathematical superiority of British ballistics over German metallurgy. The analysis demonstrated that physics principles would determine armored combat outcomes more than engineering excellence or manufacturing quality. Dr. Ernst Sauer, directing armor research at the German Army Weapons Office, had calculated the kinetic energy requirements for defeating Tiger frontal armor and compared these requirements with known Allied gun performance characteristics. His mathematical analysis confirmed that British 17-pounder guns possessed adequate penetration capability to defeat German heavy armor at combat ranges. Ballistics testing using captured Allied ammunition had verified the armor penetration performance claimed by intelligence reports from battlefield encounters. German armor plates representative of Tiger protection had been defeated consistently by British APC-BC projectiles at ranges up to 1,000 meters, confirming Allied capability to engage German armor effectively at tactical combat distances. The mathematical equation was becoming unavoidable. German armor protection could not be increased sufficiently to defeat Allied penetration capability without creating tanks too heavy for tactical mobility or mechanical reliability. Weight limitations imposed by existing engine and transmission technology prevented armor thickness increases adequate to restore invulnerability against British weapons. Production analysis revealed additional mathematical constraints that prevented German responses to Allied firepower advantages. Increasing Tiger armor thickness would reduce production speed and increase strategic material requirements that were already limiting monthly output to levels inadequate for replacement of combat losses. Alternative solutions, including improved steel metallurgy and armor design modifications, were limited by available technology and resource constraints that prevented implementation during wartime production schedules. German metallurgical advantages had been maximized in existing Tiger designs, leaving no technical margin for significant protection improvement.
The mathematical conclusion was inescapable. German armor superiority had been eliminated through Allied systematic application of ballistics expertise to anti-tank weapon development. Individual German tank excellence could no longer compensate for systematic disadvantages in the fundamental physics of armor penetration warfare. German tank commanders were forced to develop new tactical doctrine that acknowledged Allied armor penetration capabilities while attempting to maintain combat effectiveness despite the loss of armor and vulnerability that had sustained German tactical advantages since 1939. Oberst Kurt Meyer, commanding 12th SS Panzer Division, had implemented modified tactical procedures that emphasized long-range engagement, improved concealment techniques, and rapid position changes designed to minimize exposure to Allied anti-tank fire. These modifications represented fundamental changes to German armored doctrine that had previously emphasized offensive operations. German crews were being retrained in defensive procedures that had not been emphasized during the early war period when German armor superiority allowed offensive tactics with minimal concern for enemy anti-tank capabilities. The psychological adjustment was difficult for crews trained to assume tactical superiority through superior equipment and aggressive leadership. Range estimation techniques were being modified to account for Allied guns capable of effective armor penetration at distances that exceeded German expectations about enemy capabilities. German crews were forced to engage at maximum range while assuming that Allied return fire could achieve lethal hits at combat distances. Camouflage and concealment procedures were being emphasized to degrees that had not been necessary when armor protection provided adequate survival capability. German tanks were being deployed with extensive camouflage systems designed to prevent Allied detection at ranges where enemy guns achieved optimal effectiveness. Fire and movement techniques were being modified to minimize exposure time while maintaining tactical effectiveness. German crews were trained to fire quickly and change position immediately, assuming that stationary tanks would be destroyed by Allied guns capable of reliable first-hit kills. The tactical revolution represented acknowledgement that German armor advantages had been eliminated through Allied technological development. German tactical doctrine was evolving from offensive superiority to defensive survival, reflecting fundamental changes in the mathematical balance of armored warfare effectiveness. The assessment conference that would fundamentally alter German armored warfare doctrine occurred on September 15, 1944, in the secure briefing room at Army Group B headquarters. Present were the senior commanders responsible for German armored operations on the Western Front, including General Feldmarschall Walter Model, General Oberaust Heinrich Eberbach, and armored division commanders whose units had suffered increasing losses to Allied anti-tank fire. The conference had been called to address escalating German tank losses and develop tactical solutions for maintaining armored effectiveness against Allied forces equipped with weapons capable of defeating German armor protection. But the statistical evidence presented during the meeting revealed that existing problems reflected fundamental shifts in the technological balance that could not be overcome through tactical adjustments. General Major Fritz Bayerlein presented loss statistics that quantified the crisis facing German armored forces. Tiger tank losses during August and September had exceeded replacement capacity by ratios of 3 to 1, with over 60% of losses attributable to frontal armor penetration by Allied anti-tank guns. The mathematical trend indicated that German heavy tank strength would be eliminated within 6 months if current loss rates continued. Technical analysis confirmed that Allied armor penetration capabilities had evolved beyond German protection systems. The 17-pounder gun could defeat Tiger frontal armor at ranges up to 1,000 meters with reliability exceeding 80%, eliminating the protection advantages that had sustained German tactical superiority since 1941. Oberst Hyacinth Graf Stradwitz, one of Germany's most successful tank commanders, acknowledged that German crews were losing confidence in armor protection and tactical doctrine that had proven effective during earlier campaigns. Crew performance was declining due to psychological stress caused by vulnerability to Allied weapons that could penetrate previously impregnable armor. The most sobering aspect of the analysis was recognition that German armor development could not restore invulnerability against Allied anti-tank weapons. Physics limitations prevented armor thickness increases adequate to defeat British penetration capabilities without creating vehicles too heavy for tactical employment or mechanical reliability. Strategic alternatives were limited and unattractive. Defensive tactics could reduce exposure to Allied anti-tank fire, but would surrender tactical initiative to enemy forces equipped with numerical superiority and adequate armor penetration capability. Increased production could not compensate for loss rates that exceeded manufacturing capacity while requiring strategic resources needed for other military priorities. As the senior commanders concluded their assessment, each understood that they had witnessed the mathematical proof of German armor obsolescence on the Western Front. The Tiger tank that had dominated European battlefields for 2 years was becoming vulnerable not through inferior German engineering, but through superior Allied application of ballistic science to anti-tank weapon development.
The Sherman Firefly represented more than tactical innovation. It demonstrated Allied ability to adapt existing systems through incremental improvement while maintaining production efficiency and operational reliability. British engineers had solved the German armor problem through systematic application of mathematics rather than revolutionary engineering advancement. But the full implications extended beyond immediate tactical considerations. Allied forces had demonstrated that technological problems could be solved through scientific method applied to weapon development, while maintaining the industrial capacity necessary to deploy solutions at scale. The despised Sherman tank had been transformed into a Tiger killer through British ballistics expertise. The mathematical equation was becoming clear. armor thickness could not overcome projectile velocity when physics principles were applied systematically to penetration problems. The age of German armor invulnerability was ending, and Allied anti-tank weapons would soon make even the most sophisticated German tanks vulnerable to destruction by opponents who understood that mathematics was more powerful than metallurgy in determining armored combat outcomes. The scorned Sherman Firefly was about to prove that systematic engineering could defeat spectacular engineering through practical application of physics principles to military problems.
Movement techniques were revolutionized to prevent Allied targeting while maintaining tactical mobility. German tanks utilized terrain features, smoke screens, and coordinated movement patterns designed to minimize visibility during repositioning operations. Stationary defensive positions were abandoned in favor of mobile defensive techniques. Communication procedures were enhanced to provide early warning of Allied anti-tank activity and coordinate defensive responses among multiple German tanks. Radio protocols emphasized rapid information sharing about enemy positions, engagement results, and tactical modifications based on Allied firepower demonstrations. Allied forces had developed systematic tactical procedures that maximized Firefly anti-tank effectiveness while maintaining overall armored formation capability. British tactical doctrine emphasized coordinated engagement techniques that overwhelmed German defensive measures through superior firepower concentration and tactical coordination. Major John Semken, commanding 11th Armored Division tank squadrons, had implemented formation tactics that positioned Firefly tanks for optimal anti-tank engagement while providing mutual support through coordinated movement and communications. Squadron organization included one Firefly per troop, ensuring that every Allied armored unit possessed adequate anti-tank capability for German heavy tank destruction. Firefly crews received specialized training in long-range gunnery techniques that maximized 17-pounder accuracy at combat ranges up to 1,200 meters. Training emphasized target identification, range estimation, and first-shot accuracy procedures that could achieve armor penetration before German tanks could respond effectively with return fire. Coordinated engagement procedures had been developed to concentrate multiple Firefly guns against individual German tanks, ensuring destruction through overwhelming firepower rather than individual marksmanship excellence. Allied tactical doctrine emphasized systematic target engagement that eliminated German tanks through mathematical certainty rather than tactical finesse. Formation movement techniques were designed to provide Firefly tanks with optimal firing positions while maintaining protection through terrain utilization and mutual support. Allied formations moved with Firefly tanks positioned to engage German armor at maximum effective range, while standard Sherman tanks provided close support and infantry coordination. Communication systems allowed real-time coordination of anti-tank operations across squadron and regiment levels. Radio protocols provided immediate notification of German tank locations, engagement results, and tactical modifications based on enemy responses to Allied firepower demonstrations. Target prioritization emphasized German heavy tanks as primary objectives, with Firefly crews trained to engage Tigers and Panthers before addressing lighter German armor or supporting vehicles. This tactical focus maximized strategic impact by eliminating German vehicles that provided decisive tactical advantages. The systematic destruction of German heavy tanks by Allied anti-tank weapons created psychological effects that extended beyond immediate tactical consequences to influence German crew performance, unit morale, and strategic confidence in armored warfare capabilities. Psychiatric assessments of German tank crews revealed stress levels that had not been observed during earlier campaigns when armor protection provided adequate survival capability. crews who had operated with confidence in armor and vulnerability were experiencing anxiety disorders related to vulnerability to Allied penetration capabilities. German crew performance was declining due to psychological factors rather than technical inadequacies or tactical training deficiencies. Experienced crews were making operational errors caused by stress responses to combat conditions where previously reliable protection systems could no longer guarantee survival. Unit cohesion was being affected by casualty rates among experienced crews who had been considered irreplaceable due to advanced training and combat experience. Tank commanders with years of successful operations were being killed by Allied weapons that could penetrate armor protection that had previously provided absolute security. Replacement crew training was complicated by psychological factors that had not been significant during earlier training programs. New crews were aware of Allied penetration capabilities and experienced anxiety about armor protection that affected performance during training and combat operations. Strategic confidence among German armored commanders was declining as tactical assumptions based on armor superiority were invalidated by Allied anti-tank effectiveness. Commanders who had planned operations around assumptions of German tank invulnerability were forced to develop defensive strategies that acknowledged Allied firepower advantages. Allied Firefly production had achieved levels that demonstrated industrial warfare advantages over German precision manufacturing approaches. The mathematical comparison revealed how systematic application of modification techniques could overcome resource constraints while maintaining tactical effectiveness. British conversion statistics indicated that Firefly production was exceeding 400 vehicles monthly through systematic modification of existing Sherman tanks rather than complete vehicle manufacturing. Conversion time averaged 72 hours per vehicle, allowing rapid scaling of production capacity through additional conversion facilities. Quality control procedures ensured consistent ballistics performance across all modified vehicles while maintaining production speed that exceeded German heavy tank manufacturing by ratios of 8-to-1. British industrial organization had optimized conversion processes for maximum output while preserving the performance standards necessary for tactical effectiveness.
Production statistics revealed the mathematical impossibility of restoring German armor advantages through increased manufacturing. Current production capacity could deliver fewer than 200 heavy tanks monthly, while combat losses were exceeding 300 vehicles monthly across all fronts. The deficit was permanent and increasing due to industrial constraints that could not be overcome through resource reallocation. Allied anti-tank capability had reached levels that eliminated German tactical advantages regardless of crew training, tactical innovation, or operational planning excellence. The 17-pounder gun could defeat any German tank at combat ranges, while Allied production was delivering anti-tank capability faster than German industry could replace destroyed vehicles. Technical analysis confirmed that German armor development could not restore invulnerability against Allied penetration capabilities within timeframes necessary for military effectiveness. Physics principles favored firepower development over armor protection, creating permanent disadvantages for tactical approaches that emphasized armor thickness over mobility and firepower. The mathematical conclusion was inescapable. German armored warfare doctrine had been invalidated by Allied systematic application of ballistic science to anti-tank weapon development. The age of armor and vulnerability was ending, and future armored operations would be determined by firepower, mobility, and industrial capacity rather than protection systems. The defeat of German armor superiority through Allied anti-tank weapon development established patterns that would influence military technology development throughout the Cold War and contemporary periods. The strategic lesson was fundamental.
Systematic application of adequate technology could overcome individual excellence through mathematical concentration rather than revolutionary innovation. Post-war analysis revealed that Firefly effectiveness had exceeded all development projections, achieving kill ratios of 4-to-1 against German heavy tanks while maintaining mechanical reliability and production efficiency that allowed widespread deployment. The 17-pounder gun had proven that systematic ballistics development could defeat armor protection through physics principles rather than engineering complexity. German armor development had demonstrated the limitations of protection-focused approaches when confronted by systematic firepower improvement. Tiger and Panther tanks represented engineering excellence that was strategically irrelevant when facing enemies equipped with adequate anti-tank weapons produced at industrial scale. The technological race between armor and anti-tank weapons had been decided permanently in favor of firepower, establishing principles that would influence military vehicle development throughout the modern period. Nations learned that mobility and firepower were more valuable than protection in technological competition where physics principles determined ultimate effectiveness. Industrial capacity had proven more decisive than engineering excellence in determining armored warfare outcomes. Allied ability to deploy adequate anti-tank capability at systematic scale had overwhelmed German individual vehicle superiority through mathematical concentration that rendered exceptional performance irrelevant. Strategic implications extended beyond World War II to influence contemporary military planning and defense industrial policy. Modern armored vehicle development emphasizes firepower, mobility, and survivability over maximum armor protection, reflecting lessons learned from the defeat of German heavy tank doctrine by Allied systematic application of ballistics expertise. In the devastated factories of Germany and the productive facilities of Britain, the mathematical equations that determined Western Front armored warfare had been calculated by ballistics engineers rather than tank designers. The Sherman Firefly represented systematic application of physics principles to military problems, creating tactical capabilities that rendered German armor excellence strategically obsolete. The German dismissal of Allied tank capability was based on assumptions about armor protection that were invalidated by British understanding of penetration physics. German engineers had created masterpieces of armored vehicle design, but British engineers had solved the penetration problem through mathematical analysis rather than engineering tradition. The strategic lesson was mathematical rather than technological. Modern warfare belonged to nations capable of systematic problem-solving through scientific method applied to military requirements. Individual excellence could achieve tactical success, but could not overcome systematic disadvantages in industrial capacity and technological development approaches. German armor superiority had been eliminated not through inferior German engineering, but through superior Allied application of ballistic science to anti-tank weapon development. The scorned Sherman Firefly had proven that adequate equipment deployed at sufficient scale was more valuable than excellent equipment produced in limited quantities. The mathematical equation was final. 17-pounder kinetic energy could defeat Tiger armor thickness regardless of metallurgical excellence or manufacturing quality. Physics principles had overwhelmed engineering tradition, and the age of armor invulnerability was ending through systematic application of penetration mathematics rather than revolutionary tank design. German tankers had learned too late that armor protection could not overcome projectile velocity when ballistics principles were applied systematically to anti-tank weapon development. The Sherman Firefly had transformed from scorned Allied tank to Tiger killer through British engineering that understood mathematics was more powerful than metallurgy in determining armored combat outcomes.